Okay, next up we have Bryan Tan from Santa Barbara. And he's going to speak about SolType. Thank you.
Okay, hello everyone. I'm Bryan, and in this talk, I'll be presenting SolType, which is a refinement type system developed by my colleagues and I at UC Santa Barbara, UT Austin, and Microsoft Research for verifying arithmetic overflow safety in Solidity smart contracts. So first, I'm going to discuss overflow safety in Solidity, then I will walk through the key features of our type system using a series of examples, and lastly, I'll describe our implementation and how it performs in practice. So smart contracts are becoming increasingly popular for financial applications, especially those running on the Ethereum blockchain. However, smart contract bugs are very costly, mainly for two reasons. First, smart contracts typically implement applications such as currency exchanges, auctions, and investment contracts. As billions of dollars flow through these types of financial applications every single day, a smart contract bug could lead to a huge amount of monetary losses. Second, one key property of smart contracts is that once a smart contract is deployed, its bytecode cannot be modified. So it's important to get smart contracts correct before deployment because it'll be impossible to fix a bug that has caused, or more importantly, could cause, huge monetary losses. To understand where these bugs are coming from, let's first consider Solidity, which is a statically typed imperative domain-specific language that's used to implement over 90% of the contracts on the Ethereum blockchain. In Solidity, contracts are modeled as objects in the object-oriented programming sense. A contract contains a constructor as well as methods. And a contract also contains fields called state variables, which are persisted across transactions. A user can also execute a contract by invoking a method. According to a recent study, the most commonly reported type of smart contract bug is integer overflow. So that means that to guard against overflow, developers insert runtime overflow checks using a library called SafeMath. At the bottom left here is an example of the SafeMath add function, which basically just combines an add operation with a runtime overflow check. But because users are charged fees to execute smart contracts on a per virtual machine instruction basis, as they're charged for every single instruction that they run, developers are incentivized to minimize the number of runtime overflow checks. So to reduce the risk of overflow errors, this means that developers have two options. They can either pay the tax of using SafeMath for every single operation, or they can manually prove that there cannot be any overflow. But manually proving overflow safety is much more involved than just adding a runtime check. So here's an example of a token contract, which contains a mint method that allows a token owner to generate tokens. So there is an unchecked addition here on line 14. And despite the addition being unchecked, it's actually possible to prove that it's overflow safe. To see how, first note that between method calls, the contract maintains the invariant that the sum of all the values contained in this mapping BALs is at most tote. We call such an inductive invariant a contract invariant. Second, observe that any individual value of BALs, such as this BALs message.sender here on line 14, cannot exceed the sum of all of the values contained in BALs. And this is because the integers in BALs are unsigned. Third, the runtime overflow check here, or rather the SafeMath call here on line 13, combines a addition operation with a runtime overflow check. So that means that tote plus amount cannot overflow. And equivalently, that also means that tote plus amount as mathematical integers are at most the maximum machine integer. So from these three observations, it follows from the transitivity of less than equal that the unchecked addition here on line 14 is actually overflow safe. However, note that this verification task is actually highly non-trivial to the average developer. In particular, they have to guess an invariant, and they have to show that it holds across all method boundaries, and they have to repeat this process as they develop the contract. Secondly, they also need to be able to reason about integer bounds and sums over various data structures, which is tedious and error-prone. At the end of the day, developer just wants to safely optimize their contract. We observed that much of this verification effort could be automated and presented in a user-friendly way with refinement types. Our work is centered around addressing the two key problems that I mentioned just now. First, we designed SolType, which is a refinement type system based on liquid types that's specifically designed for verifying arithmetic overflow safety in Solidity. The main feature of SolType is that it contains relational algebra-like refinement terms that allow a developer to express contract invariants involving properties over complex mappings. Such properties include sums of mappings of unsigned ints and sums of mappings of structs with uint fields. These kinds of data structures are common in Solidity smart contracts. Second, we implemented SolType into a prototype type inference tool called Solid, whose function I will kind of demonstrate in the following examples. Lastly, we empirically show that Solid is useful for verifying overflow safety in the smart contract domain. Now I'm going to briefly demonstrate how Solid can be used to type check the example contract that I showed before. So first, Solid will translate that contract into mini-sol, which is an intermediate representation that we designed that is friendlier to verification than Solidity. Note that the program has been rewritten into SSA form with all data structures such as mappings and structs made immutable. So here, for example, instead of mutably updating the mapping, we actually perform an immutable update. Secondly, inspired by previous works in liquid types, state variable reads and writes are moved to pairs of fetch and commit statements, respectively, at method call boundaries. Fetch will simultaneously define local variables that contain the values of all of the state variables when this fetch is executed. And similarly, a commit will simultaneously update all of the state variables with the given values when the commit is executed. So similar to operators in previous works in liquid types, fetch and commit are designed to enable temporary invariant violation. The contract invariant is assumed to hold at a fetch and is only checked at the commit. Okay, so after Solid converts the contract to mini-sol, the next step is to generate typing constraints. So let's assume that the user provides the contract invariant as a type annotation on the state variables, namely vals, in the style of liquid types. The annotation can be read as vals is a member of the set of mappings of unsigned integers such that the sum of the mapping is at most tot. Using this annotation, Solid will generate two constraints. First, one concerning the safety of this unchecked addition here on line 13, and second, one that enforces that this user provided contract invariant indeed holds. So for the purposes of illustration, let's just consider this mint function here. So the first statement in this mint function is this fetch statement on line 7. The fetch statement will read all of the state variables simultaneously into these newly defined local variables. Solid will assume that the contract invariant holds on these local versions. Next is the .add method call on line 10. This corresponds to the SafeMath add call, which combines the add operation with a runtime overflow check. Similar to other refinement type systems, SolType tracks so-called guard predicates, which is the set of predicates that hold along the current path. In our case, the system knows that the overflow check will ensure that tot1 plus amount as mathematical integers will be at most the maximum machine integer. This property is added to the guard predicates. Then the result is assigned to tot2, which simply has the type equating tot2 to the right-hand side of this let. The next operation in the contract is an index into the mapping vals1 here on line 13. Since vals1 has unsigned integers as values, that means that the index value is at most the sum of vals1. And we see this fact reflected in the refinement type of the index operation. Okay, finally, we reach the unchecked addition here on line 13. So we need to actually check the overflow safety property here. So the system will generate a subtyping constraint that encodes the overflow safety property. During the constraint solving phase, this subtyping constraint will be encoded as an implication in the quantifier-free combined theory of rationals, equality of uninterpreted functions, and arrays. In this case, this implication can be proven valid by an SMT solver, so no overflow occurs here. The system still has to generate one more constraint to check that the user-provided contract invariant indeed holds. So after checking the overflow safety here on line 13, the system will assign the type of BALS2. The refinement type of BALS2 consists of two parts. First, we directly equate the value of BALS2 to the right-hand side of this let statement. Secondly, we can reason about the sum of BALS2 as it relates to BALS1. Namely, the sum of BALS2 is equal to the sum of BALS1 minus the old value contained in BALS1 plus the new value to update by. The SMT solver, well, not the SMT solver, but algebraically, we can see that this simplifies to sum of BALS2 equals sum of BALS1 plus amount, which is exactly what we expect. Lastly, the system will encounter this commit statement here on line 15, which will simultaneously update all of the state variables with the provided arguments here. So the system will generate a subtyping constraint that actually checks that this contract invariant holds at this point. And again, this constraint will reduce to an implication, and it just so happens that this implication here can be proven valid by an SMT solver. So the user-provided contract invariant is valid. So we've done two things. First, we've shown the overflow safety of this unchecked addition, and second, we showed that the user-provided contract invariant holds. So this contract type checks. But the problem is that the user still has to manually provide the contract invariant. Ideally, a type inference procedure, such as liquid type inference, should be able to take care of that. But type inference will only work if the developer has already inserted runtime checks to guard the unsafe operations, which defeats the purpose. Developer is only using unsafe operations because they want to avoid runtime checks. Therefore, the tool should be able to infer an invariant even if there are truly overflow unsafe operations, because either the tool or developer can just insert runtime checks where overflow safety cannot be proven, and they can remove runtime checks where safety can be proven. So we note that this type inference problem sounds similar to a constrained horn clause version of maxset, which we will kind of mention informally as max CHC. So in particular, overflow safety constraints are soft constraints, which are optional to satisfy, and all other constraints are hard constraints that must be satisfied. Because there are no existing off-the-shelf max CHC solvers that we are aware of, at least, Solidity incorporates a simple but not optimal greedy inference procedure that relies on calls to an off-the-shelf CHC solver, and the full details of this procedure can be found in our paper. For this example here, if we pretend that this addition here is actually unchecked, Solid is unable to actually satisfy the soft constraint, but Solid is able to satisfy the soft constraints for this unchecked addition here on line 13. So it actually reports that a runtime check is necessary in this case, but a runtime check is not necessary in the other case. Okay. The running example I just showed has a mapping of unsigned integers. However, many contracts typically include complex mappings, such as mappings of unsigned integers and mappings of structs with unsigned integer fields. For example, suppose that the example contract instead uses a nested mapping of uint called ax, which is a mapping of a uint. The new contract invariant in this case would be a double sum over both the kind of inner index and the outer index of all values of ax, and we would say that this double sum is at most tote. And hypothetically, if ax also incorporated structs, then the sum would become even more complicated because it would also involve a field access. So it is not immediately obvious how we should specify such sums, nor is it obvious how to generalize the terms that we generated for lookup and update to more complex mappings. So I'm going to briefly summarize our solution here. The full details can be found in our paper. The main idea is that we want to express sums of complex mappings by adding two operators, flatten and field, for nested mappings and structs respectively. And then we want to compose these two operators with the sum function. So for example, the sum of this nested ax mapping can be written as sum of flatten of ax, where flatten can be understood as transforming ax into a mapping of uint, which we can then sum over. Then we're going to modify the terms that we generated for lookup and update to reason about sums of values instead of just values. So for example, in the type of ax sub I, or ax of I, we know that the sum of values inside of ax of I, so recall that ax of I is a nested kind of like an inner mapping, We know that the sum of acts of I, and not just any individual entry in I, in acts of I, is at most the sum of all of the values contained in all of the nested mappings in X. We note that we can generate the sum terms like sum of flatten of X in a type-directed manner, and that we're not just limited to mappings of ints and mappings of structs of UN fields. We can also combine the two together. So we can have something like sum of field of flatten, etc. The full details, again, can be found in our paper. Okay, so to test the type system in practice, we implemented a prototype type inference tool called Solid. The tool takes Solidity source code as input, and then it tries to find a typing assignment that maximizes the number of operations that can be proven overflow safe, under the assumption that a developer or tool will insert runtime checks when an operation cannot be proven overflow safe. Solid contains a fully automated mode called AutoSolid, as well as a semi-automated mode called SemiSolid. The only difference is that in SemiSolid, the user can manually specify the contract invariant. We evaluated the effectiveness of our type system in two major ways. First, we assessed Solid in several key metrics, such as number of redundant checks identified, false positive rate, and running time. As a baseline, we compared to a state-of-the-art smart contract arithmetic safety verifier called VerySmart. Second, we determined the impact of using typing rules for sums, as well as our domain-specific type inference procedure. I'll only briefly summarize the results in this talk. The full details can be found in our paper. We considered two benchmark sets for this evaluation, totaling 120 contracts. The first one is called EtherScan, which is a set of contracts randomly sampled from the etherscan.io service. The second one is VerySmart, which is the set of benchmarks used by the authors of VerySmart to evaluate their tool. So in summary, in fully automated mode, Solid is able to identify 86% of redundant overflow checks, which means that developers can safely avoid inserting most overflow checks when they use our tool. Furthermore, Solid achieves a false positive rate of 20.4% when proving overflow safety, which is half the baseline, and Solid takes only an average of 41 seconds per contract, which makes the tool feasible to use during development. Solid also does better in all metrics, on average, if the user manually provides the contract invariant, as well as inserts additional annotations and assumptions. We also evaluated the importance of our type inference procedure. Solid, with all features enabled, achieves a false positive rate of 24.7%. When we set the contract invariant to true, the false positive rate increases to 48.7%. Lastly, if we perform full type inference, but we mark all constraints as hard, the false positive rate rises to almost 70%. The results here suggest that 1, contract invariants are critical for proving overflow safety and solidity, and 2, to be useful during development, an invariant inference tool focused on overflow safety and solidity should adopt a technique that's similar to our soft constraint approach here. And Lastly, we also measured the effect of disabling sums for complex mappings. The false positive rate is 39% when only sums of mappings of unsigned integers are used, while the false positive rate is 23.5% when all possible sums are considered. So this indicates that reasoning about sums of complex mappings is vital for proving overflow safety in non-trivial contracts. In summary, SolType provides simple, effective, and developer-friendly automated overflow safety verification for smart contracts. As the evaluation demonstrates, this effectiveness is only achieved by incorporating our contract invariant inference procedure with soft constraints, as well as reasoning about sums of complex mappings. Thank you for listening to my talk.
Okay, so we have some questions from the audience.
Hi, Bryan. This is Germán del Bianco from Nomadic Labs. Thanks for your talk. So I have a question and a small follow-up. So by the way that you presented your invariants, it looks like they are checked in a way execution atomically in the sense of execution. And I was wondering how you if reentrancy bugs or could be detected in your setting, or if or if you can cope with reentrancy attacks, which is a common thing in Ethereum. And so the follow-up is, can you define properties that actually depend on the execution of other contracts in your framework? Thank you.
Yeah. So if I understood the question correctly, it was how do we deal, or can we use our type system for reentrancy? And the second part of that question was, can we deal with calls to other contracts? So to the first part, our type system can deal with reentrancy. It's just that it's very kind of it's very coarse-grained. So because we're kind of atomically kind of ensuring that the contract invariant holds, it's not going to be very precise. So we can kind of block reentrancy in a way. It's just that it's not going to be very useful because we'll probably mark most things as unsafe. And the second part of that question was, how do we deal with external contract calls? So that's going to kind of be a future work. So in this work, we only considered kind of invariants holding over a single contract.
Okay, we now have a question from the online audience. So this question is from Longfam. Did Solidity pose a unique challenge on the design of SolType, or is SolType immediately applicable to other languages, including non-smart contract languages?
Yeah, that's a great question. So I think Solidity was kind of unique in that, well, I guess as far as like engineering problems, there's a lot of engineering problems trying to develop a tool for Solidity. And there's a lot of kind of interesting constraints here in that you want to be able to, you're typically dealing with a lot of money and kind of semantics related to money. And there's a huge focus on like integer variables and things like that. I believe that SolType is applicable to other languages. So the intermediate representation we designed just is kind of like a somewhat like a regular imperative language, except that also has to deal with what are basically like hash tables that don't have lookup, don't have membership operations. So yeah, I do believe it is applicable to other languages, although probably needs some work before it can be adapted to other languages.
Okay, more questions. Okay, I have a question. So this is coming from an outsider, but your false positive rate was around 25%. Can you put that in context? That sounds like it would be a lot, or is that something that you want to improve in future work?
Yeah, so it does sound like a lot. It was actually, so we look here, here's the 25%, 23.5%. So there's a lot of like crazy arithmetic heavy contracts out there, and there's a lot of simple ones. And for those crazy, crazy like 1,500 line contracts, then we can kind of, so one of the main weaknesses of SolType is that it relies heavily on this contract, on being able to infer the contract invariant. And so if it cannot infer the contract invariant, then it will generally kind of do very poorly when it tries to identify redundant or unsafe, or when it tries to prove the safety of operations. So if you look at, I think, some competing tools, you can see that the false positive rate is kind of around that area, or you can always add more complex benchmarks to even lower to increase the false positive rate. I hope that answers the question.
Yes, thank you. We have one more online question. So this question is, how hard would it be to extend the specifications to aggregate functions other than sum, such as average or min-max? Do you know whether such additional functions help rule out false results?
Yeah, so that's another great question. So we think it'd be pretty easy to extend it to min and max. So sum was just one example that we considered in the paper, and we found that it was enough to prove most overflow safety in the cases that we looked at. We think min and max, yeah, min and max are used for a few, are used in a few contract invariants that we saw. And so I think it would be pretty straightforward to extend the system to min and max, as well as other kinds of properties. Yeah.
Okay. Oh, one last question.
Hey, thanks. Cool talk. I don't know much about smart contracts, but now I want to learn. So when you're doing both the after the fact statistics and when you're doing the maximum satisfiability problem, do you have any sense of weighting static calls to the expensive functions by the number of times it could execute at runtime, or is every static call counted equally?
Sorry, could you repeat the question?
So do you, when you're performing the satisfiability, do you weight the cost of inserting an expensive add, for example, by the number of times it could execute at runtime, or is every static call to an expensive function treated equally?
Oh yeah. So currently we just assume that they're all treated equally, and then I think that's an interesting idea, trying to weight the calls. But the problem is that you don't have any kind of profiling data to work with because you can only deploy your contract once, right? I hope that answers the question.
I think I'll stop here. Hopefully you'll be around online so that you can follow up with some questions in the lounge. Other than that, we have a break here. So that's the end of the session. So let's thank Bryan again.